School Halloween. Just got a little liquid nitrogen in the spoon here. I'm hoping to catch a Leidenfrost star. It's just like like a brass spoon or something like that. I just got it set up here. I'm trying to see if that's going to form a Leidenfrost star for us. Oh yeah, there we go, baby. Just like that. Look at that. You can see it. I can't tell how many lobes it has. Oh, it's a little tough to see now. Let's pour a little more in there. That worked pretty well. Here we go. Let's add a little more liquid nitrogen. The puddle size is a little too small. All right, in it goes. If you look closely, you'll see a little bit of bubbling. Yeah. Come on, man. Come on, baby. Let's see it again. Just a little bit's got to evaporate off. And when we get to the right size, I see those lobes starting to form. Maybe not. There it goes. Come on, come on. There it is. We got a Leidenfrost star. It's way too many lobes to tell. Boy, it didn't last long, did it? Man, that didn't last long at all. How you doing there, School Halloween? Welcome aboard. I am trying to create some Leidenfrost stars with liquid nitrogen. So I'm pouring liquid nitrogen into this spoon. It should boil away quick. Oh, there it is. There's another one. Look at that. It's got 5 lobes. You can totally see it. Totally see it. Very cool. All right. Let me add a little more here. So here goes the liquid nitrogen into my spoon. School Halloween, welcome aboard. We are trying to create some Leidenfrost stars. We got a whole lineup of liquid nitrogen experiments for you today on the Tommy Technetium channel. Welcome to the live. Hope we have a good time together. Hey, two-timer, welcome back. You can see the edges. So that's just some liquid nitrogen in a spoon. It's a brass-colored spoon. And as the nitrogen boils, it forms a vapor barrier beneath it, and those vapor barriers form bubbles that pulse. And if the frequency, thanks there, two-timer, there it is! If the frequency of the bubble pulses matches the frequency of the Leidenfrost star, it forms. Having a little bit of trouble getting this one going here. I think that you could see that big, large bubble pulse. I think that kind of disrupted the pattern. You can see some ice crystals in there forming too. Hey, look at that. You see that little 5-star? Come on, baby. Come on, little 5-star Leidenfrost star. It doesn't last long. Let's add a little bit more liquid nitrogen here. Here we go. We'll do this a couple more, and then I'm going to do some blue morpho butterfly experiments. Hey, thanks there, School Halloween. I'm glad you liked that one. Which I do a lot of Scrub Daddy shorts. You're going to have to let me know which one you like, School Halloween. All right, so we got liquid nitrogen in a spoon, and as it boils, there's some gaseous pulsations that occur on the surface between the liquid nitrogen on the bottom of the droplet and the spoon, and if those pulses hit a certain frequency, it'll set up a wave pattern in the droplet, and that'll actually form some geometric shapes. You can sort of see some lobes forming. Yeah, I can totally see them. And look at that. You can totally see there's like, it's going too fast. It's easier to see look at that. Oh, we had a really interesting one there for a while, and then that big bubble disrupted it. Yeah, I can put some liquid nitrogen on paper. Let's do that, all right? Let's go ahead and do that. Can you see the ice crystals in there? See the ice crystals in the droplet? They start to build up in there after a certain amount of time. Yeah, we'll put some liquid nitrogen in some paper here. Come on, I think we're going to get the 5-lobe star. There it is. All right, that's enough of that. Let's see some liquid nitrogen on some paper. All right, back this off. How cold is that? That's pretty cold, but it's not too bad. Okay. There. Here's the planned experiments for today. Light and frost stars, what I kicked everything off with. Let me turn this upside down like this. So I'm gonna pour some nitrogen in there. Yeah, we start off with some light and frost stars. We're going to work with the blue morpho butterfly wings. I'm going to put a sparkler in liquid nitrogen today. That's really interesting. There's some very interesting chemistry that happens when you put a sparkler in liquid nitrogen. Sorry about this. I'm trying to get my tripod set up here. One more. So I got a little more control. Nice. Okay. I'm also going to maybe get out my superconductor. We'll mess around with that. I'm going to put some LEDs in liquid nitrogen, and this is because we're going to do some experiments that you all suggest, like putting liquid nitrogen on some paper. Let's give it a shot here. Here we go. You can see it wets the paper. Yeah? Can you see over here where the paper has been wetted? And then it evaporates away. Pour it on there. You can see the paper has been wet by the liquid nitrogen. Yeah? And then as it warms, it should evaporate away. It's easier to see. It's easier to see. Happy Sunday there, Johnny. Happy Sunday. It's easier to see if I do it with blue morpho butterfly wings. So that's what we're going to do next. I'm just going to go ahead and pour some liquid nitrogen into this bowl here. And I'm going to add a blue morpho butterfly wing. See, you can see it's nice blue color. And when I dip the wing in there and pull it out, you can see that the nitrogen changes the color of the wing. And then as the nitrogen evaporates away, you can see that the color changes back. Now, the reason why this happens is because inside the blue morpho butterfly wing, there are these finger-like structures, projections that they call lamellae, and they have a certain distance in between them. And in between, they're like this, okay? And then in between these structures, there's usually air. And the protein structures interact with light in a particular way, the light and the air in the spacings. And it does so in a way that it amplifies and reflects blue light extremely well. However, if you can fill those spaces with something other than air, that's going to change the way the wing interacts with light, and therefore it's going to change its color. So when I fill the wing with some liquid nitrogen, the color changes. And you can totally see the nitrogen evaporate away. And as the nitrogen evaporates away, the wing just goes back to its regular color. And it's interesting to note that can I make liquid hydrogen rainbow? I apologize. I don't know what you mean by that. What's interesting about these wings, however, is they don't get wetted by water. Liquid nitrogen wets the wings, but water does not. What do I mean by this? Well, you can see that the liquid nitrogen soaks into the wings, it sticks into the wings, and then evaporates away, of course. But if we try this same experiment with water, let's see what happens. A little bit different, I'm thinking. Let's give it a shot and see. So there's the wing. We'll zoom in so you can see just a little bit better what I'm doing here. And I'm going to add some drops of water. Give me a second here. I got to get a little bit of water. Okay, add some drops onto the wing. Here we go. And watch what happens. You see how the water beads up on the wing? Let's get a little close up. The water beads up on the wing. And that's because remember I said these wings have little tiny finger-like projections all throughout the wing. You can kind of see that it's got like a really strong surface structure to it. You see, if I really zoom in, look at that fine structure. And those are a lot of little nooks and crannies in the wing. And because of all those little nooks and crannies, the water, in order to wet the wing, is going to have to spread out into all those tiny nooks and crannies. And water has a high surface tension, and so it can't do that. It's not going to spread out into all those little tiny pores. Hello there, Lucifer. How are you? And because it can't spread out into those tiny pores, it just beads up and falls right off the wing like that. Isn't that cool? Very beautiful. It's kind of like a magnification effect there with a droplet of water. Now, liquid nitrogen has a low surface tension. So liquid nitrogen has a low surface tension. So if I try this same experiment, let me get the water off so it doesn't freeze. If I try this same experiment with liquid nitrogen, we're going to see a different result. Of course, I got to get some liquid nitrogen. Hold on, I ran out. All right, here we go. All right, in goes the liquid nitrogen. And you can see it soaking into the wing and also changing the color of the wing. That's because those little tiny pores are usually filled with air. Naiku, it's a blue morpho butterfly wing. Now the tiny pores in the wing are usually filled with air, and the pores, the structure of the pores, the physical structure of the pores, and the air inside interacts with light in a particular way that makes it appear blue. But if I fill those pores with liquid nitrogen, then the way the wing interacts with the light makes it appear green or greenish blue rather than blue. I don't have any liquid hydrogen. That takes extremely high pressures. So yeah, I don't have any liquefied hydrogen. Sorry about that. Sorry, I don't mean extremely high. I meant metallic hydrogen is extremely high pressures. I don't have, that's really cold. So you can see there the liquid nitrogen is, excuse me, soaked in the pores. So Lucifer says, how about alcohol? Pardon me, it has a lower surface tension than water. Would it work like liquid nitrogen, or is it still too much? Let's find out. We're going to do this for Lucifer, all right? So this is for Lucifer. We're going to take some alcohol. I'm going to get some 91% rubbing alcohol. Excuse me, I got to go over in the lab over here and grab a little bit. All right, Lucifer, this is for you. See, I got my 91% isopropyl alcohol. We're going to add a little bit of this onto the wing. See what happens. Remember, it has lower surface tension, and sure enough, the alcohol with a lower surface tension also fills the pores, and because the alcohol is different than the air, it's going to stay soaked into those pores, and it's going to change the color of the wing. Look at that gorgeous green color we got. Let's add some nitrogen just to see what happens. If we freeze, let's see what happens if we freeze the alcohol in there, just for the heck of it. I mean, that should change the structure of the alcohol. Maybe it'll change the color further. I don't know. That's why we do the experiment, to find out. That seemed to turn like a brown. That was like a dud, man. It did, Lucifer. It sure did. Yeah, I don't think the wing's too happy right now. We're going to leave it out for now. And I'm going to let that stuff evaporate off. And we'll come back to that later. We'll come back to that later. What we're going to do now, I think, is mess around with LEDs. Let's mess around with LEDs and liquid nitrogen. This is crazy cool. You guys are going to love this stuff. All right, let me get my liquid nitrogen here. Back the camera up just a bit. Okay. And let's get some LEDs going. Pour this in here. All right, I'm going to need to turn the lights off for this. We're going to do the green one. Green or yellow? I think it's yellow. We're going to do yellow first. Yellow works really well. All right, lights out. Okay, folks, I've got my yellow LED, and I'm going to dip this down into some liquid nitrogen. Hello there, orange. Down it goes. As it cools in the liquid nitrogen, you might notice a color shift. You see that? Come on, baby. Come on, man. Look at that green. Isn't that beautiful? That is so freaking cool. So the yellow LED drastically changes to a green color when you chill it in the liquid nitrogen. Isn't that beautiful? Absolutely beautiful. Yep. And then as it warms, it should go back to... Try to warm it back up. As it warms, you'll notice it's going back to a more yellow color. Hey there, Angelo, what's going on? Isn't that beautiful? Now we're back to yellow. So as the LED warms, thank you there, Angelo, it's back to yellow. We're going to stick it down in the liquid nitrogen and watch what happens. Look at that, it's shifting to a green. Isn't that gorgeous? That is absolutely gorgeous. Take it back out, let it warm up. How you doing there, Glenn? Warm that back up, and it should shift from its green back to the yellow color. I'll tell you what, drop an emoji in the chat, a heart emoji in the chat, or any emoji of the color LED you'd like to see me pop in next. I have red, I have yellow, I have green, and I have blue. Red, yellow, green, or blue. Looks like we're already doing yellow, and you can see the color shift there. Down it goes again, so it's in the nitrogen. In the nitrogen it goes. There's that shift to a green color. It is just gorgeous. Do acid with liquid nitrogen. Woo, baby, look at that green shift. Johnny wants red. Johnny, I saw you first, so we're going with red. Try with a bunch all at once. And orange juice says blue. I'm going to do red next and then blue. All right? So I'm going to take the yellow one out. Here's my red one. All right, here we go. Red LED and liquid nitrogen. Welcome back, Angelo, excuse me. All right, let's see what happens with this one. Red LED, down it goes into the liquid nitrogen. Let's see what happens. Let me know if you're seeing a color shift. All I'm seeing in my end, I'm seeing it go really dim and a little bit more orange, but it's really tough to see. Really tough to see the effect, but it's a lot dimmer. Interesting. Could you swim in liquid nitrogen at its low surface tension? Give me a thumbs up if you could actually see this shift to a orange color. Give me a thumbs down if you think I'm crazy that I think I see a shift to an orange. I think it's there, but it is subtle. It is dimmer, so it's a little tough to tell. I'm going to warm it back up, and we'll see if we can see that nice red color again and see it get warmed back up. Johnny agrees with me. Says, yeah, it's a little more orange than it was before, and now it's a lot redder. Subtle. It's a subtle shift. Let's do blue. Let's do blue. The best shift is the yellow one, which is why I do it first. We're going to go with blue. Pardon me. And then we're going to let's stick a sparkler in liquid nitrogen next, shall we? You guys want to do that? Give me a thumbs up. Here we go. Does it burn? It would if I left my hand in there, but I don't do that. And I don't even stick my hand in there. If I do it real briefly. I've done that before. Here we go. All right, here we go. In goes the blue LED. In it goes. You can hear it. I don't know about you, but that looks a little bit more violet than it did before. What do you think? I think that's a shift to a more violet color. It is definitely more dim, for sure. Definitely more dim. I'm going to warm it back up, see if we get... Yeah, that looks more violet than it did before. Light green. I'll do green next. Yep, you got it, Angelo. And you can see it's getting more blue as it warms back up. So all of these are kind of shifting to bluer, you know, to the violet as they're cooled down. All right, let's try the, who said green? Angelo wanted to see green. And then we're going to do, of course, the encore. We'll go back to yellow, because yellow is the best, man. Yellow is the best. If you haven't seen yellow, you're definitely going to want to stick around to watch it. Here we go. Here's a little bit of green. The green LED. Looks kind of like a yellow-green on the camera right now. All right, down it goes. Let's see what happens. In it goes, cooling down. I'm saying that looks maybe more yellow, huh? I think that looks more yellow. Boy, that's cold on my hand, man. Woohoo, baby. I don't like leaving it down there too long. Yeah, that looks more yellow to me. A little bit more yellow. It won't, it stops working if I put the battery in. But the LED, well, let's find out. I don't know the administrator, let's do it. Let's just stick it down in there. The problem is that it conducts, so the battery starts getting really cold, and then that makes my fingers cold. But I'm going to stick this down in there as long as I can. As long as I can handle it. So that is pretty much the temperature of the liquid nitrogen right now. Has it completely gone out? It has not. It's still glowing. Oh man, it's just barely glowing. But it's still there. It still has a little bit of glow to it. Just a bit. Yeah? You can see the condensed water vapor coming off of it. Why cooling down dims the light? Well, you know, what's interesting is sometimes it makes the light brighter because the conductivity increases as temperature goes down. But sometimes it also obviously makes it dimmer because the, you know, I don't know. I don't know why it gets dimmer, to be honest with you. I would think that it would get brighter as it cooled because the conductivity should increase. But I don't know why it's getting dimmer. All right, let's do the yellow one. The yellow one is really cool to see. Here we go. Yeah, you got it, Park. Here we go, Park. Welcome back, Orange. So here we go, the yellow LED. Let's put that down in there. Watch what happens. Yellow LED and liquid nitrogen. You're going to love this color shift. Come on, man. Look at that. Look at that. Look at that gorgeous green color as the LED cools in the liquid nitrogen. That is just really cool. Thank you there, Evan. And then when I take it out, because my hands get, look at that. Look at how you see the liquid or the condensed water vapor coming off of it. And you can watch it come back to its yellow color as it warms back up. Isn't that cool? Too thematic. Thank you there, Orange. It's cool there, Spy, isn't it? Very cool. That's back to yellow. Oh, man. And then we're gonna send it back to green. Here we go. Down in the liquid nitrogen. Ooh, baby, that's chilly. Keep my fingers out of that. And look at the shift to green. Thank you there, Tophomatic. All right, you guys ready to put a sparkler in liquid nitrogen? I don't have a purple one, School Halloween. I apologize. Beautiful green color as it chills. Thank you there, sir. Okay, let's put a sparkler in liquid nitrogen. Because you know why I'm doing all these liquid nitrogen experiments? Because it's liquid nitrogen month on my channel. So I put out, I think I've got 2 or 3 videos already this month with liquid nitrogen stuff. All right, we're going to move around to the hood. So here is the hood. Let me turn the lights on so you can see what's going on. We got to make sure we do this experiment in the hood. You can see I've got a beaker here. I've got my blowtorch. That's how I'm going to get my sparkler going. All right, I do have neon bulbs. All right, let's try this. What do you think will happen if you stick a sparkler in liquid nitrogen? That is what we're going to find out. Niku, what temperature scale do you want to know? So liquid nitrogen is 77 Kelvin, negative 196 degrees Celsius. That's negative 321 degrees Fahrenheit. I'm going to put some liquid nitrogen into this beaker. Give me a second here. Okay. Let's get some lighting back there so it looks a little nicer. Hey, welcome everybody to the Tommy Technetium channel. Thanks for hanging out. We're doing some liquid nitrogen experiments because it is liquid nitrogen month on my channel. And of course, I'm going to do a lot of experiments with liquid nitrogen. We got to put this up, make it look pretty. Yeah, that'll look nice. Gives it a nice little flair to it. All right. All right, here we go. I'm going to pour some liquid nitrogen into this container. And it boils rapidly. That's because if liquid nitrogen hits anything above negative 321 degrees Fahrenheit, it's going to boil. Or negative 196 degrees Celsius. Rotate the glass a little. Give me a second. I got to get my gloves on. Rotate the glass a little for frames. Is that how you want it, frames? Give me a thumbs up if you like it. That look good? I don't know. I'm going to lower the camera just a bit before we get this started. What I'm going to do is I'm going to put a sparkler in liquid nitrogen. Put a thumbs up if you think the sparkler will go out. Put a thumb down if you think the sparkler will continue to burn. Thumbs up if you think the sparkler will go out in liquid nitrogen. Well, I guess it should be the opposite. No, never mind. Thumbs up if you think the sparkler will go out. Thumbs down if you think the sparkler will continue to light. So SPY says it's going to keep lighting. Leaf Tube says it's going to keep lighting. Some says it's going to keep lighting. Orange says it's going out. Aha, Frame says no because of the Leidenfrost. We got some physicists in the chat. Arena says it's going to remain. Go out. Sir says it's going to keep glowing. Josh says it's going to keep glowing. Let's find out. So here we go. I got my sparkler here. Let's get that baby going. And we're going to pop it in the liquid nitrogen and see what happens. Here we go, baby. And it goes. Look at that, man. It's still glowing. Come on, man. And notice, you're going to see something else. That is a sparkler that is going in liquid nitrogen. And you might notice the color of the liquid nitrogen has changed as well. Do you see how it's yellow now? There's some major chemistry going on there. See, in the sparkler flame, it releases nitrogen oxides. So that's like NO2. And NO2 happens to be a brown colored gas. But in the liquid nitrogen, it's not a gas, it's a solid. So I have trapped some NO2 solid in the flame, in the liquid nitrogen. Here, we'll do it again. Here we go, we'll watch it again. All right, so I'm gonna light the sparkler. Here it goes. And remember, the sparkler gives off NO2 gases. Look at that, it's still lit, baby. Come on, man. That sparkler is still lit, and you'll notice that the nitrogen's taking on that yellow color, and that is from the NO2 gas that the sparkler's giving off. And as the NO2 gas goes into the liquid nitrogen, it freezes and forms a yellow colored solid. Hey, thank you there, Rod. So here, we're going to continue to watch this, because you might notice as the nitrogen continues to boil away, you might notice that this yellow color becomes increasingly, the yellow color is going to become increasingly green. What the heck? Why might that be happening? Well, here's why. It's because the liquid nitrogen, the sparkler doesn't just give off NO2. That's one of the gases that it gives off. It also gives off nitrogen monoxide. That's why I did this in the hood. So it gives off both of these gases. The NO2 is usually a brown colored gas, but it's yellow in the liquid nitrogen, okay? The NO is colorless. So that does not contribute to the color, okay? However, these two things react and they form N2O3, which is blue in color. So the NO2, the NO2 and the NO that have frozen in the liquid nitrogen, they react and they form blue N2O3. And that's why you're noticing this shift to a green color, because the yellow colored NO2 is reacting with some colorless NO to form the blue colored N2O3. Here, we'll add a little more. We'll put another liquid or sparkler in there. For those of you just joining, I'm going to take this sparkler and I'm going to put it in some liquid nitrogen. We're going to see what happens, okay? Give me a thumbs up if you think this will continue to burn in the liquid nitrogen. Give me a thumbs down if you think it'll go out in the liquid nitrogen. How to make N2O, I do not know. Is the reaction in equilibrium? Quantum burger. As long as we're continuing to see changes occur in here, it's not at equilibrium, right? At equilibrium, everything stays constant. And because I'm noticing this is continuing to get more green in color as the reaction proceeds, I think we're making more N2O3. We're going to let this all boil off, because when all this boils off, you will be able to see the crystals of N2O3 and NO2 form on the bottom of the flask. I am a chemistry teacher, Naiku. Here we go. So Mrs. Cook says it's going to keep on burning. Here we go. We're going to take this sparkler. I'm going to get it lit. I'm going to pop it in there. We're going to see what happens. Here we go. By the way, I'm doing this in the hood. This is done in the hood. Look at that, man. It's still burning down there. Come on, man. Come on, man. That's cool. I got to tell you, man, the first time I saw that, it blew my mind. I did this the first time. I thought, it'd just be fun for
the 4th of July. You know, people light sparklers on the 4th of July. I thought it might be fun to celebrate the 4th of July by sticking a sparkler in liquid nitrogen. Look down in there, man. It is still going. Come on, man. It is still going. Out it goes, all right? Out it goes. Come on, Japul, I see ya. I see ya. Are there going to be green crystals? We're going to have to find out. Some thought. Thank you there. Excuse me, sir. It's, well, orange, I would say yes, the solids are crystallized in here, but they're, you know, I think they're probably suspended in there. Tell me about it, Lucifer. X-Steel, I know, man. Isn't it cool? Oh, gosh. I think NOS is NO2. Somebody correct me if I'm wrong about that. Somebody asked that in a comment. This is going to take a while. This is going to take a little bit, so we have to wait for all of the nitrogen to boil off to be able to see it. So you'll notice, so the reason why this happens is because the sparkler gives off, when it's in there, the sparkler gives off NO2 gas, which is brown, but it looks like yellow when it's in the liquid nitrogen. The sparkler also gives off NO gas, which is colorless. So these two things react. NO2 and NO react to form blue-colored N2O3. So if you have a yellow-colored solid and the blue N2O3, together it's going to look more blue. Thanks, Sir Mark Bishop. I'm looking for the, so it's nitrous oxide. Is that N2O or NO2? I think that's, I can't remember off the top of my head, Mark. So N2O3 solid is formed. That's correct, Quantum Burger. I have an article that's going to come out on this probably in just a week or two. No, I am not, Evan. I am doing this experiment in my hood, just so you know. I'm doing this in the hood, okay? So this experiment is being done in the hood. That's the hum that you hear in the background. Evan, I don't think I'm going to try that during a live, but if you have suggestions for how to do that safely when I'm not doing a live, I'm happy to hear your thoughts. But yeah, that's just a beautiful chemical reaction. Can liquid nitrogen be freezed? It can, Naiku. You're going to want to look through some of my more popular YouTube shorts. If you put it in a, if you put liquid nitrogen in a vacuum chamber and lower the pressure, you can freeze it. How about it, Quantum Burger? You just send me an article, or excuse me, send me an email, and I'll send it to you when I get it. So, Polly, what I'm doing here, I'll show you, Polly. What I've done, I should say, is I took a sparkler and I put it in a lit sparkler. I put it in some liquid nitrogen. It kept burning down in there, and it formed something that looked yellow at first. But as it continues to the nitrogen continues to boil away, you can see that's looking green, and that's because the sparkler gives off two gases. One of them is NO2, which is yellow in color in the liquid nitrogen. Another one is colorless. So how do we get the green? Well, the colorless NO gas and the yellow-colored NO gas, they react to form something blue. So yeah, so we get this yellow-colored gas. I know I have brown written here, but it looks yellow in the liquid nitrogen. This yellow-colored gas reacts with the NO. Both of these are emitted by the sparkler. And when it gets, the sparkler emissions go into the liquid nitrogen, they freeze. But these two things react to form N2O3, which is blue in color. Look at that gorgeous green, man. That is really cool. Haha, funny, Peter. I wouldn't think a liquid, what you're saying there, would look green. I'd think it'd be another color. Hello there, orange. So we're just waiting for that. Does what give off? Does it give off any odor? Yes, Quantum Burger, it does. So NO2, NO is odorless, but the NO2 smells kind of nasty. If you've ever seen like a school bus drive by, and there's sort of like an acrid odor that you might smell in the exhaust from the school bus, that's from the NO2. I don't mess with cyanide, Larch. Funny there, Jacob. So going in liquid nitrogen must be a pretty slow reaction. Oh, yeah, that's nitrogen triiodide, Evan. We're getting close. We are getting close to the point where we're going to see the crystals form. So I need to get things set up so you can see it. It's very interesting, in my opinion. We definitely don't want to see that. I'm going to put a white piece of paper down here. Yeah, Evan, I am doing this in a hood because the NO, I mean, look, I'm being extra careful. I'm doing this live, so I'm making sure that I do everything really safely, which is why I'm doing it in the hood. The NO2 and the NO gases are not good for you to inhale. But, you know, you do it outdoors and you know what you're doing, you can probably get away with it. Okay, I'm going to now stick this up on the white piece of paper so we can watch the crystals form. Look at that gorgeous blue, man, like a greenish blue. Come on, baby. Come on, look at that. Evan, what I did is I know this might be crazy, but I made this thing that you're looking at, this fluid, by taking the sparkler and putting it into some liquid nitrogen. I'm doing extra hour at work there, Polly. Let me put this up here so we can see just a little bit better. You know, that angle isn't quite the way I like it. Let me try to get this just a little bit better. I think maybe I'm going to just stick it right up on top. This might work even better. Here we go. I'm just going to stick this right up on top. See how this looks. Give it a little bit of... And there we go. Come on now. Yeah, that's a little hard to see. I'm not liking that. We got to get this crystal. Whoa, baby, that would have been bad. That would have been bad. That would have ruined the experiment. There we go. There, I think that's good. Yeah, we can see what's going on there. Yeah, you can totally see the frost on the outside of the beaker there. What are the properties of N2O3? Mark Bishop, it is used as a rocket propellant. So it is used, you know, the different oxides of nitrogen have been used as in rocket fuels. I think they're used as oxidizers. I do, Polly. I'm a physical chemist, so I got my PhD working on the biophysics of photosynthesis. You can do this liquid yourself. You can if you have access to liquid nitrogen. So if you have some liquid nitrogen, you can take a sparkler. You can light the sparkler and dip it down into the liquid nitrogen, and it'll start off looking yellow, but as you can see, as the liquid nitrogen boils off, this is looking increasingly like a blue color. And we're waiting, because I'm waiting to see the crystals. I want to see if this... I think that looks a little better. What do y'all think? You can see the nitrogen boiling out. Hello there, orange. So long, orange. Yeah, it looks nice. That's what it looks like from the top. I think this is the best way here. So long, orange. Great hanging out with you today. We got some more experiments ready for you after this one here. It's getting close, though. It is definitely getting close to where the crystals are formed. You can see that the nitrogen is really boiling away. And when it boils away, those crystals are going to appear before your eyes. So MTTZ, it gives off nitrogen oxides because sparklers contain nitrates as an oxidizer. And some of those oxidizers only get partially reduced. So some of them get reduced into, you know, the NO2, various forms of nitrogen oxides. User, you hang around, you're going to see Mr. White, I promise you. Maybe sooner than you think. When will the reaction increase when you add pressure in a vacuum chamber? I think it would decrease, it would go slower. We want the liquid nitrogen to evaporate off quickly. You and me both there, stars, you and me both. Hello there, Benji. We're almost there, folks. We are almost there. You can tell that nitrogen is almost boiled away, and when it does, you're going to see some crystals form on the bottom of that beaker. Now, in my experience, the crystals are green at first, and that's because it's going to be a mixture of the NO2, which is yellow, and the N2O3, which is blue. Doing well there, Tennessee. However, those green crystals often shift to blue as the NO2 evaporates off first, leaving the N2O3 behind. So Benji, what we are looking at is the residue after I put some spark. Here, it's getting ready. It's getting ready. I'm sorry, the nitrogen's almost evaporated away. I'm going to turn this light on. We got to get this focus right. We got to see it, baby. Come on now. Come on now. Here come the crystals. Pretty close there. Pretty close there, MT. Here they come. Come on, baby. The last of the nitrogen's evaporating off. Let's see those. There they are. There they are. You can see them form. There's the crystals. There are the crystals, baby. Come on, man. Look at that. So actually, those crystals look blue to me. So those are mostly crystals of N2O3 that have formed on the bottom of the beaker. Now, look at that. Isn't that gorgeous? You might notice a color shift from green to blue as the NO2 evaporates off. Yeah, they're fairly reactive. Now you'll notice the crystals are getting smaller in size because remember, these substances are gases at room temperature. And so they're going to go back to the gas phase. Samph, I have not tested that yet. Can you smoke it? Come on, man. Hey, they're blue crystals. What can I say? And so you can tell those crystals are evaporating away, probably sublining. There may be some chemical reactions going on. Look at that gorgeous blue. Look at that shift to a gorgeous blue color. I hear you, Herbie. And we might be able to see that they've gone back to NO2 gas here in a moment. I agree, Key. It is a, look at that gorgeous blueness. Come on, man. Come on, man. Isn't that fun? It's one of my favorite experiments. And you know what I love about it? I gotta be honest. I invented this experiment. And so it just, it just tickles me. Thanks there, Benji. I appreciate that. What's the goal here, Eddie? I'm just goofing around in the lab, man. Look at that gorgeous blue. Look at the blue. So the N2O3, that's the blue stuff that you see. It's a solid, but as it warms, it's going to go back to NO2 gas, which is a brown color, and it's also going to go back to NO. Pretty much, stars, part of it. That's right, N2O3 is rocket fuel. Benji, we got some more stuff we're going to do. It did, Satori. It arranged like itself in a pattern. It is not copper sulfate, I-. It is N2O3, which you can make simply by immersing a lit sparkler into some liquid nitrogen. So Kim Jong, what I did is I took a lit sparkler and I immersed it in some liquid nitrogen. This is the residue that we found after all of the nitrogen evaporated away. It's crystals of N2O3. You might start to notice a brown color forming. That is the N2O3 going back to NO2 gas, which is brown, and NO gas, which is colorless. Seattle, I'm not really a synthetic chemist. This is the best synthesis that I've ever done in my life, and all I did is stick a sparkler in liquid nitrogen. I'm going to go ahead and try to get some of the crystals, the ice crystals off of the flask. I want you to see that. I can totally see the brown gases starting to form. Oh, I-, I'm always up to something. I'm always up to something, doing some science, I-. Here we go. So I want you to look at this beaker. I'll turn this off. I think you might be able to see just a little bit better. I'm going to start warming this with my hand. And you might notice that the beaker is going to be like a little bit more brownish in color. And that's because the N2O3, look at that. You can totally see it. See that brown color? That's the N2O3 going back to NO2 gas and NO gas. So the NO2, that's the brown color gas. Hey, thanks there, Goofy. Appreciate it. You know, Nightmare, I think it's a chemical change that's going on. Thank you there, Quantum Burger. I appreciate that. Let's talk about it real quick, and then let's get back to some other experiments. So what? Here, you can totally see it in the beaker. Look at that brown gas. Come on, baby. Look at that brown gas. So what happened? What happened? The sparkler gave off NO2 gas and NO gas. It's brown and colorless. Those reacted to form the N2O3 blue-colored crystals, and then this reaction goes in reverse when it gets warmed up. That's why we got the brown-colored gas back again. Isn't that cool? So the dinitrogen bond is diluted by the oxygen, making it MTTZ. I'm gonna have to think about that question a bit. I don't have that. I don't have it. The Lewis structures in my head. I'm gonna have to think about that. Is it denser than air? Yes. NO2 is more dense than air. Not quite, Rackster. That's not something you'd want to be emitting. All right, let's get back up to some Taco Bell gas. Let's get back to some liquid nitrogen experiments, shall we? What am I doing next? You guys want to see the superconductor? You want to go back to doing LEDs? You want to do blue morpho butterflies? Give me a stoplight if you want to do LEDs. Give me a butterfly if you want to do the butterfly experiments. And give me a magnet if you want to do the superconductor experiments. Pop your emoji in the chat for what we're doing next. Magnet for superconductor. Stoplight for LED. Quantum Burger wants to see the superconductor. Herbie wants to see the superconductor. Well, those are the 2 votes. That's what we're doing. Let's get her going. Yep, Goofy wants to see him. Okay, so what I'm going to do back here is I'm going to take... All right, most people want to see the superconductor, so that's what we're going to do. Give me a second here. So embedded into these plastic pieces is what's called a type 2 superconductor. Superconductors expel magnetic fields, okay? Superconductors expel magnetic fields. But type 2 superconductors have impurities in them. So you can imagine there's like a thin wafer of a superconductor in here, and they have impurities. The magnetic field can penetrate the impurities. So what happens with these things when they're placed in well, they got to be superconducting, so I have to cool them. But when they end up getting placed, pardon me, in a magnetic field, the field lines penetrate the impurities, and it ends up locking the superconductor in place. So that's what we're going to see. Let me get I got to get my magnet system out here. Excuse me just a second. It's going to take a moment. All right. Up. France. There we go. All right. Sorry I wasn't quite ready for this. I didn't think we were going to do it, but we're having a good time, so let's get rolling. Okay, so here is my magnet. This is like a circular magnet here. Here's my superconductor. It doesn't do a whole lot at room temperature. You can see the block magnet system here. It's not doing a whole lot either. Let me zoom out a little bit so we can see just a bit better. There we go. All right. Not much happening with the magnet at room temperature. But if we cool this system in some liquid nitrogen, we get this cooled below its critical temperature. This will behave like a superconductor. So here we go. Let me get some liquid nitrogen. Pour it into that bowl back there. Miss. Swing and a miss. Try again. Here we go. All right. So the superconductor's critical temperature is 92 Kelvin. So if we can cool this below 92 Kelvin, it'll behave like a superconductor. So in it goes. Liquid nitrogen 77 Kelvin, so that's more than cold enough to chill it beneath its critical temperature. Usually, it sinks when it's where it needs to be. There it goes. It's sunk. Let's get these in there too. Get that one in there. Get this one in there. There it goes. I want to see if this sticks to the magnet. It does. I need a spoon that doesn't stick to the magnet. Let's see if this one does. Yep, that one does too. That's not going to help me. Oh, looks like I'm going to need to use my glove. All right, here we go, baby. Let's get this superconductor out first, chilled beneath its critical temperature. And we're going to stick it right there and watch her go. Very nice, huh? Come on, man. Look at that. We're messing with a superconductor there, Faith. Let's turn her upside down. Look at that. So the magnetic field is penetrating the impurities in the superconductor. And because of that, it locks it in place. Here, we'll do it over on this side where the magnetic field changes if you get outside of the little rectangle. Look at that. You can see the space in between the superconductor. Here, we'll give it a little tilt, and we'll turn that baby upside down. And look at that. Yeah? Very interesting, huh? Move it back over here. Oh, it's starting to warm up. It's starting to warm up, so it's losing its, you can see it. It's losing its ability to behave like a superconductor. So we're going to pop that back in there to get it cool below its critical temperature. Oh, tell me about it, Quantum. Come on, Quantum Burger. Tell me about the applications. Can you imagine the maglev speed trains they'd have over in Japan if this thing could work at room temperature? Come on, baby. Get this thing working. Folks are trying to do just that. All right, let's pop this right there. Look at that. Why do they need to become so cold to become a superconductor? So, Hardy, what needs to happen is the electrons in the system need to pair up into what are called Cooper pairs. And that only happens at low temperatures. Look at that. So again, this is a type 2 superconductor, which means there are impurities in it. And so the magnetic field penetrates the impurities. And once it's penetrated those impurities, it's locked in place. Because in order to move it, you have to move the field lines from through the impurities to through the superconductor. And remember, superconductors expel magnetic fields. They don't like them. They don't like them going through them. And that's why they call this quantum locking, because of those impurities allow those field lines through. And once those field lines are going through the impurities, man, that baby's locked in place. What are you buying? You're not buying anything free, man. We're just having a good time, man. So, you want to buy something, you can go ahead and subscribe to my channel if you like. But, that's up to you. If you like science, I'm your guy. This is known as quantum locking. Yeah, I have if you want to check out my long form videos, I got a video on what is quantum locking. This is kind of fun too. Let's see if we get a magnet balanced on this. This is fun to do. We can get it going. Give me just a second. All right. Quantum science is new science. Yeah, it's about 100 years old now, though, at least. All right. Let's try this, baby. Come on now. Let's do it with this. Put my brick here. Okay. Let's get that one cold. I don't think that one's ready for us. Let's get this one back out. Put this upside down. Get this magnet going here. Ah! Come on now. Lock in place. There we go. Come on, man. We got it. That just looks like science, doesn't it? Huh? Watch this. Oh, look at that, baby. That's cool. Isn't that cool? It's just a magnet hovering above a superconductor. I'm rotating it. So this superconductor's been chilled below its critical temperature. The magnetic field lines, as long as they're penetrating the impurities in the superconductor, and as long as they continue to do so, the magnet's free to move as long as the field lines continue to penetrate the impurities wherever they're doing so. What in the Dexter's lab am I watching? That's just one of the comments for now. Tell me about it, Stars Forward. I'll tell you what. Let's just say I'd kind of say that, you know, science gets people in trouble today, huh? Isn't that gorgeous? Isn't that gorgeous? What holds it left to right? I apologize, I don't understand the question. Let's see, let's watch. So you can tell that the superconductor is warming. You see the crystals forming here. That's where ice is starting to form. And notice, the superconductor is warming, and as it warms, it's being raised above its critical temperature, and it's no longer able to support the magnet because this is now above its critical temperature. So we've got to chill this again to get it to work. Let's get a fresh one out, one that's been in the liquid nitrogen for a little while. That's kind of neat to see, isn't it? When the, you know, as you watch the superconductor sort of, well, you can't really watch it warm, but you can see the magnet sink as the superconductor loses its ability to expel the magnetic field. That's called the Meissner effect. Okay, let's see here. Pop it on like this. Ooh, a little nitrogen boiled off. There we go. Watch this. Let's see if I can, maybe. Oh, I want to see if I can get the magnet. Look at that. See that? You can pull it up. You can totally pull it up. Isn't that wild? Isn't that wild, man? Look at that. It's just goofy. I did not make the superconductor, Izzy. It is a IBCO superconductor, however, made of the elements yttrium, barium, copper, and oxygen. Okay, now you can see once the ice starts to form, it starts to lose its ability to do its superconducting stuff. And as you watch that, as it continues to get ice on the surface, it'll, you know, get above its critical temperature, and that leaning tower of magnets should fall. By the way, this is the Tommy Technetium channel. It's liquid nitrogen month on my channel. I'm doing lots of experiments with liquid nitrogen, cooling these superconductors with liquid nitrogen right now. I see you, Marty. Great comment. Vibrational frequency ran through liquid or crystals. It's not magic, it's magnets. Love it, Izzy. Boy, that's really staying locked like that, which is odd. I would have expected that to fallen by now. What is happening? I don't know. I don't know. Some YouTuber claiming this is how the pyramids were built. That is really staying up there for a long time, which is confusing me. I do not know why that's interesting. Interesting. I am confused. I got to be honest with you, folks. I would imagine this is above its critical temperature right now, and that thing is still locked in place. Look at that. Maybe I'm wrong. Let's just keep it. We'll keep it there and see. How long will it take for the leaning tower of magnet to fall? Could you theoretically create a track of superconductors that are liquid cooled like a computer, but is with liquid nitrogen, then move a magnet over it? Is that how they can make a train system? Well, I do have, like, there it goes, it fell. I do have a magnetic track that I stick these guys on. This is kind of fun to use. All right, let's get the next one going. Let's try this little thin one. The issue with this experiment is, as the experiment proceeds, the superconductors take on water. And as the crystal takes on water, they don't work as well. Come on, man, that's just beautiful. Look at that. That's really kind of cool. But this one warms up quite quickly. You can see that. You can see the ice forming across the surface, so we know it's warming. And when that gets warm enough, those magnets are just going to sink. It's hovering yet. Hello there, Chevy. Water, that's right. Water coming from the water in the atmosphere. That's correct. There it goes. It's above its critical temperature, and it's no longer able to expel the magnetic field. Hey, thanks there, Noel. I appreciate the subscription very much. Thanks there, David. All right, here we go. Let's put it on the big old track, shall we? Let's put it on this track here. See how this works. Get this up here. Chilled in my liquid nitrogen. Of course, I got my tongs are magnetic. Ooh. Almost hurt myself. Oh, it's so hard to get off. Oh, okay. Look at it go. Hello there, Insa. That's kind of fun. It's making me dizzy, man. Oh, I love it. Moto Smack. Come on, baby. Bill Nye, the dry ice guy. I love it. I love it. You win the comment so far for today. What a great comment. What I am doing is I am chilling superconductors, type 2 superconductors in some liquid nitrogen, because it's liquid nitrogen month on my channel here, on the Tommy Technetium channel. So I'm chilling some superconductors in liquid nitrogen, and then we're messing around with them. We did some other experiments earlier. Here, let me show you an experiment that we did earlier, just for the heck of it. We do all sorts of stuff. So another experiment I did is I took one of these blue morpho butterfly wings, like this one right here. Watch what happens when you dip this thing in liquid nitrogen. Here we go. Come on, baby. Look at that color shift. Yeah? And then watch as the nitrogen evaporates away. You can totally see it evaporating away. Come on, man. That's just... We talked about that. We also stuck a sparkler in liquid nitrogen and the sparkler in liquid nitrogen. It keeps burning, man. We talked about that. We made some chemical compounds. So, yeah. Yeah, I don't think they're not using superconductors in the Japan trains. So that's the kind of stuff we've been doing. We also did this. Here, let's do this too, in case you're just brand new. You're going to like this, promise you. This is another thing we did today. I'm going to take a yellow LED. We're going to stick it down in some liquid nitrogen. You're not going to believe what's going to happen. And then I want to show you something I just learned this week that I thought was kind of interesting. Really fun experiment. All right, let's do the yellow LED experiment. Got to turn the lights out for this one. You get a nice superconductor out here. Get that back into the... There we go. I might need a refill on my nitrogen. All right, let's get that yellow LED burning. Turn out the lights. You're going to love this. All right. Yellow LED versus liquid nitrogen. Here we go. Yellow LED, down into the liquid nitrogen. See if you have this on your bingo card. And it goes. Ah, come on, man, look at that. What color was the LED? Are you sure it was yellow? Was that a yellow LED I put in there? Because it sure looks green to me now. Isn't that beautiful? Isn't that crazy? And then watch, we'll take it out. Remember, it's green now. It's green in the cold. We're going to take that baby out. We're going to let that thing warm. I'm going to warm it up. You can see that, condensed water vapor coming off of it because, it just looks sciencey, doesn't it? And look at that. We're back to yellow, just like that. Huh? Isn't that cool, Moto Smack? Thank you there, Virtuous. There, let's back in it goes. Get the yellow in. Going to green. Going to green. Thank you there, Stacy. Let that baby... Wait, how does that work? Well, we can talk about how it works if you want to do that. It's basically this. So LEDs are made by these things called semiconductors. And semiconductors have what's called a band gap. So there's a bunch of electrons. There's a bunch of electrons in something that we call the valence band. So this is like the energy of the valence band. And then up here at a higher energy level, that's the conduction band. Okay? And what happens when you put, electricity into a LED, you promote electrons from the valence band up to that higher energy conduction band. And when these electrons drop back down, they give that energy off as light. And the color that it gives off depends on the energy difference between the valence band and the conduction band. So there's electrons down low. The electricity puts the electrons up high. The electrons up high drop back down, give off energy as light. And the color of light that's given off depends on the difference in energy between the high energy electrons and the low energy electrons. Well, what happens when you cool this is you lower the energy of the electrons in the valence band. And that's because the atoms get closer together. So they just get lower in energy. That makes sense. You know, you cool something down, they get lower in energy. And because you change the energy of the valence band more than the conduction band, that changes the energy gap. And if it changes the distance between the energy gap, it changes the color. That's it. That's correct. You can stars forward here. You can watch it here real quick. Real quick. Got a little liquid nitrogen in there. You can see it. And I just pop my hand in real quick. And nothing happens. Light and frost effect, baby. Thank you, Triangle. Thanks for the question. All right, let me show you this last thing. Let me show you. I'm having a great time today. By the way, in case you're wondering, why'd the wing change color? Just in case anyone likes, older chemists in their, in their 50s, like and make blue crystals with. I made blue crystals with sparklers though. Sparklers and liquid nitrogen. I don't break bad, man. I'm not gonna break bad. That's not me. That's not what I'm about. But it's kind of fun to dress up the part. What do you think? Anyway. Anyway. Oh, I love it. I love it. Yeah, at the end of the live, I flip the camera around. I talk to you guys in my Walter White hat. If that you like that kind of thing, we'll talk for just a bit. This is a fun little experiment here. Just learned it this week. It's kind of fun to see. We're going to take this metal pan here, and we're just going to pour some liquid nitrogen into it. I think I need to make a YouTube short on this at some point. Yeah, AJ, you're changing energy gaps. Nah, stars, is that? I don't know if I'm going to do that. That seems a little iffy to me. Maybe I'll try it. I don't know. Okay. Last little bit before I flip the camera around and talk to you all for the day. I'm just going to pour some liquid nitrogen into this pan here. It's a metal pan, and it's kind of interesting, I think. Kind of interesting what happens, I think. But I'm a nerd. What can I say? Okay, here we go. In goes the liquid nitrogen. This is just a cake pan, and it goes. You see it boil? Yeah, you can see, look at all those bubbles. Beautiful bubbles. And watch what happens when the liquid nitrogen gets the pan to the same temperature as the liquid nitrogen. Look at those beautiful bubbles. Boom, there it goes. It's like smooth as silk. So what you saw there at first was rapid boiling because the pan was really hot. And so the liquid nitrogen boils very rapidly. Once the pan gets about the same temperature as the liquid nitrogen, then the boiling doesn't happen as quickly. So that's just a cool little experiment I like to do. Thanks there, Motosmack. I appreciate that. Give if you want, give a subscription. My channel's been hurting lately. I don't know what YouTube did to the algorithm. It's been killing me. So yeah, maybe share the live with folks. That'd be a little helpful. All right, let's flip this camera around. Let's talk to y'all. Let's get the right glasses on though. There we go. I got my t-shirt on for liquid nitrogen month. Liquid nitrogen, when low T is not a problem. And then you see that's the chemical formula for testosterone. So when you get to my age, low T becomes a problem. But low T, low temperature, that's not a problem when you're playing with liquid nitrogen. I know, it's just goofy nerd stuff. Thanks, there, Motosmack. I appreciate that. Love it. I love it. Yeah, it's liquid nitrogen channel on my month. So, liquid nitrogen month on my channel. So, yeah. If you like that kind of thing, I'm going to be dropping a new experiment on liquid nitrogen every week. I usually put out my new YouTube short on Saturday, 8 a.m. Eastern Time. That's when the new one comes out every week. So yeah, thanks for hanging out. I had a great time with you. You guys made this a lot of fun. You really did. Unknown must have an unpaired valence. It does, MTZZ. Definitely does, MTZZ. And hey, I need to remember to look up the Lewis structures of these different compounds that I'm forming. It's crazy. I've written a paper on the thing. You asked me a question. I don't even know. I don't even have the, my brain can't access the Lewis structures. Hey, thanks, Sir Virtuous. Great to hear. You're welcome, Daniel. Do minerals fluoresce different? Let's find out, man. Let's find out. AJ just asked an interesting experiment. Do I have the materials here? I don't. Crap. AJ, I'm sorry. I don't. However, at the end of this month, I do have a video, a YouTube short that's coming out that does show that certain things do fluoresce or maybe phosphoresce differently when submerged in liquid nitrogen. So be looking for that. And once I roll out that YouTube short, I'll do some of those experiments live for you. Those are a lot of fun. You're going to enjoy that. All right, AJ, next time. Hey, thanks for hanging out, everybody. You really did make it a lot of fun. I loved all the questions. I loved all the suggestions for experiments. I'm really happy that I was able to do some of them. I apologize for the ones that I couldn't get to do. Oh yeah, fume hood, baby. We did an experiment in the fume hood. We did an experiment in the fume hood today. Oh, got to remember to close the sash. That's like leaving the windows open. Yeah, so hey, what happened? Oh, Virtuous, I'll tell you what, go back through my YouTube shorts. You'll see a video, a whole short, it's rather long, that explains what happens when you put a sparkler in liquid nitrogen, okay? Hey, thanks, Sir Motosmack. I'll tell you what, I'm going to sign off for now, but hey, remember to take some time and look at the beauty that's all around you. I mean, it's just like always there. Science is all, like scientific phenomena. It's just everyday phenomena. And it's beautiful if you take the time to look at it. I mean, just looking at a flower. A flower is science. A flower is beautiful. I look at my partner. I think she's beautiful. There's science in that, eh? And in my opinion, when we look at the simple things in everyday life and are captivated by the beauty and wonder of it, that beauty and wonder is deepened when you understand the science that's behind it. It just deepens the beauty. It deepens the wonder. It deepens the mystery. You stick the beauty and the understanding together and you got something special. And that's something that science has to offer the world. So anyway, something to think about. If that's your cup of tea, you might like my channel. Consider subscribing. I really appreciate everyone being here today. It's been my dream since I was a young man to be able to do science experiments for people. And so you just being here today, it helping this old man make his dreams come true, even as he continues to age. And that's not something I take lightly. So thank you, everybody. Thanks for letting me do this for you. And I'm going to see you next week. All right? All right. Have a great week, everybody. So long.